All right, so welcome to part 4 of the video lecture series on Introduction to Computer Networks. So we'll talk about network transmission and the different delays which come along with it in this part. So when we're talking about network transmission, a host sends some data to another host, the source to the destination, and in this process the host breaks down the data into what we call packets. These packets are then forwarded through the network from routers to routers until they reach the final destination. The rate at which these packets are forwarded through a network is specified by the transmission rate, which is a property of the link. To be specific, we defined this earlier as the bandwidth for the link, which defines the rate of transmission. So based on the concept of the transmission rate, and given a specific packet, we can calculate the delay that this transmission will take. So let us assume that we have a host which wants to send a packet to another host, and we know that the data is defined to be as X number of bits. For a given network and the associated protocols, the packets which are created from the data has a maximum limit of the size of the packet, which is denoted here as L number of bits. So therefore the number of packets would be X divided by L, and we would get the number of packets, and this is a ceiling function. So in other words, a ceiling function means that you take the rounded integer on the top. So for example, 300 divided by 2 is equals 150, which is a rounded number. However, 3 divided by 2 is 1.5. So if we say that we want to take a ceiling value, which we show with this symbol, so 1.5, the ceiling of this would be equal to 2. So this is what the ceiling means. Next, for a given link, we have the transmission rate, which is denoted by R, and the unit is R bits per second. So therefore, if a packet is being transferred from the host to the router, it will be transferred at a rate of R1 bits per second, from here to the next at R2 bits per second, and from here to the final destination at R3 bits per second. For any given link, the delay for each individual transmission link is calculated as L divided by R. So let us look at an example. So we have a network where we are trying to send some data from the source A to the destination B. The size of the total data is shown as 700 megabytes. And for the given network, the packet size is 100 megabytes. for the three links, we have three different transmission rates, R1, R2, and R3, and they are 2.5 megabits per second, 4 megabits per second, and 3 megabits per second. One thing that you should note here is the uppercase and the lowercase b. The lowercase b is a bit, the uppercase b is a byte. And we know the relation between a bit and a byte is that 1 byte is equals to 8 bits. So given this, we are now to find the number of packets, n, and the total transmission delay from A to B for the data of 700 megabytes through the three links. So let's try to work it out here. So first of all, the data size x is equals 700 megabytes, and the packet size, the maximum packet size, L, is equals 100 megabytes. So therefore, the number of packets n is equals to x divided by L, which is 700 divided by 100 equals to 7. Alright, so now we know n. Next, we would like to calculate the total transmission delay d from the source to the destination A to B. So first, we know that L is equals 100 megabytes, which is equal to 100 times 8 equals 800 bits. Given that R1 is equals 2.5 megabits per second, we would now need to calculate transmission delay D1. The reason why we converted the size of the packets to bits is because the transmission rate R1 is expressed in megabits per second. So therefore D1 is equal to L by R1, therefore 800 divided by 2.5, which is equals to 320 seconds. Next, R2 is equals 4 megabits per second. So therefore D2 is equals L by R2, which is 800 divided by 4, and is equals to 200 seconds. Finally, R3 is equals 3 megabits per second. So therefore D3 is equals L by R3, 3. So therefore 800 divided by 3 is equals 266.67 seconds. So far we have calculated D1, D2, and D3 for one single packet. So therefore, the total delay from A to B for one packet is D1 plus D2 plus D3. This comes to be equals to 786.67 seconds. So therefore we had n equals to 7. That means there were a total of 7 packets. So therefore dt, that is the total transmission delay, is equals 7 times d, which comes to be at 5506.69 seconds. So this is our final answer for D, the total transmission delay for the total data of 700 megabytes as it is being transferred from host A to host B. So the transmission delay is not something which is only incurred by a packet as it is transferred from the source to destination. There's something that we need to understand as well, is what we call the queuing delay. So what happens here is that as the packets are being sent from the hosts to the connected routers, the router would then receive the packet and then forward it onwards to the next link. So therefore, if the incoming rate of the packets into the router is higher than the outgoing rate, these packets suffer from what we call a queuing delay. So what happens is that they are placed in a queue, so they are sent one by one as long as the outgoing link can accommodate the outgoing packet. However, as the packets are being placed in the queue, they are being stored into the router's memory, also called the buffer. So if the buffer becomes full and the hosts are still sending in the packets, there is no more place for them to be placed in the queue. So therefore these packets are dropped, and that is what we refer to as packet loss. So going forward, if you would like to consider all the possible delays that a packet will encounter, the total delay, we call it the nodal delay. That means when a packet is being sent from a host to a node, that is a router, and then sent forward to the ongoing link, the total delay that the packet incurs at this given router. So the first one is what we call nodal processing. So in this case, the router first checks if there are any errors in the packet and also determines the outgoing link. So to understand this, let us assume that we have a router and we have multiple connections to and from the router. So let's say host A is sending in a packet to the router. The router first needs to check if there are any errors in the packet in terms of the bits during the transmission. If they look okay, then the router needs to decide which of these links would be the forwarding link for this given packet. So let's say this is the link which is chosen, and therefore the packet is then forwarded on. So this whole process results into what we call the processing delay. The next delay is what we have already looked at, is the queuing delay, where a packet may be required to be placed in the queue given that the incoming link actually has a much higher transmission rate than the outgoing link. So therefore there is a backlog and therefore they need to be queued. The third kind of delay is the transmission delay, something that we already looked at, and we also did an example problem. This is the time the packet takes to be transmitted over the link. This is based on the packet length and the bandwidth of the link. Finally, we consider the propagation delay. So the propagation delay is actually based on the physical property of the transmission, where we look at the length of the physical link and also the propagation speed at which the signal can go forward. Which means that if you are using a longer wire, it would just take longer, or a packet will travel slower through the air for a wireless network compared to a wired network, which will have a much faster propagation speed. So therefore, the total delay, that is the nodal delay, would be a summation of the processing delay, the queuing delay, the transmission delay, and the propagation delay. So, as a packet is being transferred through the network, the bandwidth is one of the primary characteristics of that media. However, we also need to understand the concept of throughput. So throughput can be expressed as the effective bandwidth of a connection. So let's say if a connection has a bandwidth of 100 megabytes per second, the throughput would actually be equal or less than 100 megabits per second. So this gives us the effective rate at which the bits are being transferred from the sender to the receiver. And we generally consider two cases for throughput. One is instantaneous, which means the throughput at a specific given moment of time. This is not really interesting for us because we are in most cases interested to understand the average throughput of the network, which implies the transmission rate over a longer period of time. So basically, you capture and measure the effective bandwidth or the effective rate of transfer over a period of time t, and then calculate the average of it. The reason why the throughput is not the same as the bandwidth is something which could be easily understood by the picture here. So let's say we have two connections. The first one being this, then there is a router node, and then the next link which is of a higher capacity. So if we are trying to send data packets through the first link, it can only be transferred at the rate that this link will allow. So, although we have a much higher capacity for the ongoing link, it can only transfer at the rate at which the router actually receives the packets from the first link. So therefore, the overall effective rate of transfer is affected by the bandwidth of the first link right here. So if we have two links, RS and RC, and we know that RS is less than RC, the average end-to-end throughput from the sender to the receiver would be RS, because the router will not be able to send anything to the second link more than what it has received from the first link. So therefore the effective bandwidth is RS. In the second case, if RS is actually greater than RC, so in this case the router receives more packets, but it has a queuing of the packets because it cannot transfer it to the second ongoing link at the same rate. So therefore, with the overall transmission of the data, RC limits the overall end-to-end throughput. That is the effective bandwidth. And if we try to look into a very simplified internet scenario where you have, let's say, 10 connections sharing a link capacity of R, and if you look at the diagram, you have some servers which are connected through the link capacity R with connections of capacity RS, and then there are clients which are connected to the internet backbone with link capacity RC. So in this case, the average throughput for this overall network would be the minimum of RC, RS, and R by 10. So the minimum of RC and RS is kind of evident from the example that we saw here. R by 10 is because the link R is being shared by 10 connections. So therefore, it's R by 10, which is basically the share for each of these connections, and then RC and RS. The minimum of this would be the average throughput for the simplified internet scenario.